Okay, so this is an introduction to signals and systems, and this is part 3 of this presentation. In this presentation, what we'll do is we'll take a look at some very commonly used functions that are used to demonstrate certain whether properties or concepts within signals and systems. The first one that we look at is the impulse or delta function. Second one that we look at is the step function. Third is the rising exponential, and then the falling or decaying exponential. And then we'll take a look at sinusoids. All right, so let's start first with the impulse function. The unit impulse function is defined as a pulse with an infinite height but a zero width. Now, because it has an infinite height and a zero width, then the area of that delta function or that impulse function is understood to be it's understood to be equal to 1. In equations, it's often represented by the delta, the Greek lowercase delta, um, uh, alphabet letter or letter, okay? And by n, we use n for discrete time and we use t for continuous time. Graphically, it's represented by an upward arrow with a magnitude of 1. So again, if we look at the equation or mathematically, we have that delta function. In this case, we're talking about discrete time. So we have the delta function, discrete time, we use n. And what we're saying here is that when n is not equal to 0, the value of the delta function is 0. And when n is equal to 1, the value of the delta function is equal to 1. So when n is equal to 0, then the delta function is equal to 1. Okay, graphically, we have an arrow pointing upward with a magnitude of 1, and that's how we represent the delta function graphically. Okay, now this is a mathematical definition and cannot be produced in the real world. There's no way to produce a true delta function. Okay, because remember it'll have to have an infinite height and an area of 0. And how do you get a pulse with a area or width of 0, right? Okay. But the closest thing that we can get to the impulse function can be represented in the real world. The closest thing anyway is just a short pulse with a finite, okay, magnitude, with a finite magnitude, not with an infinite magnitude as we stated here and with a 0 width, okay? So that's the impulse function. We also have the step function, the unit step function, and we use the lowercase u uh, to represent that. And in this case, I'm sticking with the discrete time. So I do use of n or u of n, okay? And is defined as being equal to 0 for n less than 0, and it's equal to 1 for any value or for all values, that's the best way to put it, where n is equal to, or pardon me, greater than or equal to 0. So that is the unit function or step function, pardon me, in discrete time is 0 when n is less than 0, okay? And it's equal to 1 when n is greater than or equal to 0. And we represent the unit step graphically with a function or a graph that looks similar to this, where this is 0 at this point here, okay? And so we just have this and it goes on forever and ever out this way, all right? So now let's look at the falling or decaying exponential. So decaying exponential, and in this case we have a causal, it's causal and its asymptote is approaching 0. The equation for that, okay, we can say is equal to f of t, and in this case we're actually using continuous time. So it's f of t is equal to k times e raised to the negative at times the unit step. And the reason why we made it unit step is because we want this to be causal. We don't want anything prior to 0 being used, okay? And this is defined as long as a, or this is true as long as a is greater than 0, okay? And in this case that we showed here, okay, in this case k is equal to 1. And so that's why when t is equal to 0, all right, which makes this go to 1, then 1 times 1 gives us this value right here, okay? All right, so that's the falling or decaying exponential. Now let's take a look at the rising exponential. With the rising exponential, in this case, we're going to make this causal, and we're going to have this, in this case, the asymptote y is equal to k. All right. And so what the asymptote means is it's approaching a certain value. Okay. So in this case, again, we're doing continuous time. So this is f of t is equal to k times the following quantity, 1 minus e raised to the negative at times ut, or the unit step. And again, we're using the unit step because we're saying that this is causal. Okay, we're explicitly saying that it's causal. And this is true as long as a is greater than 0. And again, in this case, k is equal to 1. Okay, so that constant is equal to 1. So what you'll notice here is that it begins from 0 and it rises and it approaches the value of k. And in this case, k is equal to 1. So the asymptote is equal to 1. All right, so that's the rising exponential. That's the rising exponential. All right, so let's look at the sinusoid, which is the last one that we'll take a look at. So the sinusoid, and we're making this again causal, so we're not looking at anything before 0. Okay, and that's mathematically that's represented by f of t is equal to a sine omega t plus or minus theta times the unit step. Okay, where a in this case is a constant and it represents the maximum or minimum amplitude. So in this case here for this, a is equal to 1. That's why we have 1 here and minus 1. It's maximum and minimum amplitude. Okay, omega here is equal to the angular frequency, and that's actually equal to 2 times pi times f. Okay, 2 times pi times f. And then theta is equal to the phase shift, and the phase shift is going to determine whether this is going to be shifted to the left or to the right. Okay, so if it's minus theta, then we expect that this is going to be shifted towards the right. Okay, and delayed. If we have plus theta, then we expect that it'll be shifted to the left, and we're going to have it advancing in that case. Okay, so that's the sinusoid. So this was an introduction to signals and systems, and this was part 3 of this lecture. If you missed part 1 and part 2, you can look those up on YouTube. They are on my YouTube channel at youtube.com/CA Letsum PhD PE. Thank you.